Well, all the curiosity up front is, why is this down lower, so it's interfering with seeing the slides. And this is a display for, obviously, the meat science group. And that is a rail where they'll put a carcass on. But the rail comes through here. That has to be lowered so it lines up and goes across. So it does go up and down. We don't have the faintest idea how to make it go up and down. How's that? Food chemistry, we don't tend to use it very much. So anyway, we'll move on. So we've been obviously dealing with flavors in various ways. So giving you kind of a broad overview, sampling different topics, and we're currently on on oxidation off flavors that occur in foods. And so this is where I think we ended up talking about lipid oxidation. It is, like I say, the most common means of off flavors occurring in foods. It's just a problem. It doesn't take much lipid to end up causing us a problem. So, and again, those are the sensory characters. And I forget what I've told you and what I haven't, but anyway, when we have done this in flavor class or in short courses, we've always made each of these off flavors. And so you got an opportunity to smell them and taste them. And really, they can be pretty disgusting when it comes right down to it. It's one of those things that you'll never forget. You taste something that's really oxidized, you'll remember it. You'll remember the character. And so as we go through it, so you get a broad exposure to these off notes. And I'm an analytical chemist, largely by training, but I think I like people. And you know, if somebody tastes something and says it's oxidized, man, they've had that before, they don't forget it. That's what it is. I don't need $1 million piece of equipment to justify that or validate that. You do remember these when you taste them, believe me. So anyway, going on to a next source of off flavors, non-enzymatic browning. You know, this non-enzymatic browning is desirable. We take advantage of it in our cooking of foods. You know, where does the flavor of coffee, chocolate, maple syrup, bread, all these places. Non-enzymatic browning can give us beautiful, beautiful flavors. But again, put it down at room temperature, storage temperatures, the kinetics, the pathways change, and they change to things that aren't pleasant at all. And so most foods really have this potential as well. Most foods have potential for lipid oxidation. They have a potential for non-enzymatic browning. And you know, George again will talk about this, and he'll talk about it more in detail. And what George is going to tell you relates to off flavors. When he tells you the non-enzymatic browning increases under these conditions, that's leading to off flavors. And so we're very much in agreement. We disagree in terms of forming good flavors. No matter how long you heat a bunch of things together, it's not going to turn out like chicken or beef or coffee unless you really work at it. Off flavors come naturally, no problem at all. They form. So water activity, low to mid-range is really a problem. So if you've got semi-moist foods, pasty-style foods, they are especially prone to non-enzymatic browning. Anything that's stored under higher temperatures, it can be in a warehouse, it can be in shipment, it can be at home for that matter. Temperature will certainly accelerate it. A major issue too are sugars. What type of sugars? Basically, this is a reaction between reducing sugars and proteins. And so what are reducing sugars? Glucose syrups, high fructose corn syrup are major sources, but lactose, milk sugar, also is an issue. So we've typically got reducing sugars around as well. So like I say, it's really a common issue. What are sensory descriptors? The same darn start off, stale. Again, as I said, what's stale? It just isn't fresh. It just isn't right. And that's a common starting point for both lipid oxidation and non-enzymatic browning. So there's something wrong. You can't put your fingers on it yet. Gluey. Now, you're the wrong generation to know the brown casein glue. But again, when I was a kid, that's what we had. It was kind of a brown, clear liquid, fairly viscous, had a rubber top, and you'd slide it on your paper. That was actually the perfect example. Taste that, and it would remind you exactly of this type off flavor. Again, today we can't taste our glue or rip our cardboard up and chew on it for various reasons. How's that? All of them good. But the idea of old milk, old casein, sodium caseinate, probably old dry milk is one of the best examples of its character. So, again, very, very characteristic. Enzymes, plants, animals, they are, of course, loaded with enzymes. Because you pick the plant, because you slaughtered the animal, doesn't mean those enzymes aren't active. They still are very active. In terms of plants, a couple enzymes are really issues. The biggest ones are lipoxygenase. Lipoxygenase attacks your polyunsaturated fatty acids. It will give you very characteristic off notes. Soy is plagued by this character. It's really common that soy protein, soy-based products will have a beany character. And it comes from the natural lipase enzymes in the soy. They're involved in metabolism. They're very desirable. However, when that plant comes to the end of its life and we put the right conditions, or let's say the not right conditions maybe, that lipoxygenase enzyme will attack the fat and it will give you very characteristic beany notes, character notes. You'll also find that oats, and it's interesting, oats are one of the other products that really will pick up a rancid note. And I have to mention that rancid is oftentimes used in two different contexts, two totally different reactions. Oftentimes, or let's say much of our industry will talk about something being rancid. They're very commonly talking about lipid oxidation. But if you're in the oat business, if you're in the dairy business, rancid means something entirely different. The rancidity in dairy products and in oats comes from lipase activity. So oxidized notes appear, can come from lipoxygenase. You might call it rancid, but this also, the lipase enzyme, gives you a rancid character. But this comes from fatty acids. Lipase present in the dairy product or in a plant that comes in is mixed with a dairy product. The lipase enzyme will attack your fatty acids, breaks off the fatty acids, and you get a very characteristic off note. In dairy products, it's sometimes defined as kind of sharp, biting, cheesy character. And so that's a very characteristic off flavor that comes from dairy products. It's interesting that coconut gives you what's known as a soapy off flavor due to this same enzyme. One of the first consulting projects I worked on was on pina colada. I developed a real favorite of pina colada in the summertime. How's that? It was a good research project. I always wanted to work on wine. That's never worked out. Pina colada is the closest I've come. But anyway, coconut products. The pina colada is a mixture of pineapple juice and of coconut milk. And coconut contains a lot of C12, lauric acid, the fatty acid. Coconut fat, for some reason, tropical oils in general, contain a lot of lauric acid. And lauric, if it's free, chopped off that fat molecule, it tastes soapy, just like you put a bar of soap in your mouth. And so the pineapple was bringing in lipase, mixed that pineapple juice with the coconut, lipase attacked the coconut. But their problem was they weren't heat treating it adequately to inactivate that lipase. And so there was a very common soapy character to their product. Once they heated it well enough to inactivate the lipase, the problem went away. I oftentimes say, and maybe that comes up later on, if you taste a product and it tastes soapy, you generally got two options. The first option is there's a coconut or a tropical oil present. That's what you look for on the label. Is there tropical oil present in that food product if it tastes soapy? If it is present and it's soapy, you know what to look for. You look for lipase coming from some plant tissue, inadequate heat treatment. The second source of soapiness is a tough one. Somebody left soap in the line, how's that? They didn't rinse it adequately, they didn't clean it out adequately. So enzymes, there's many other problems, but these two are the most common. Either lipoxygenase activity, giving you an oxidized character, or a lipase activity, giving you a rancid character. Cheesy, sharp biting, any dairy products, soapy. You find lipase acts on other products. It isn't just dairy and coconut, but most of our other fats, most of our other oils have really long chain, well, not quite that long, but let's say long chain fatty acids. The lipase chops them off, but they don't have any flavor to them. It's only the short chain acids that give us flavor. So where does lipase come from? Dairy products contain them themselves, so potentially a dairy product mistreated can develop that character. But also spices, plant tissues, other plant tissues. Microorganisms can bring in lipase. Other foods, as I mentioned, pineapple. So it's a fairly prevalent enzyme that must be inactivated during the process someplace if you're going to have tropical oils present. In terms of light-catalyzed reactions, what happens when you put a food in light? We've got two unique things that happen. Certainly light is energy. Light promotes oxidation. So, okay, if you set a food in the sunlight, it's going to be oxidized in one way or another because of the energy from the light. But these are two unique off flavors that developed. One is in milk. If you expose milk to light, back in the olden days at one point, milk used to be in clear glass bottles, pretty hard to find today. They tend to be in opaque or completely blackened cartons, so no light gets through those cartons. And the reason is any kind of light from display cases, as I said, in the olden days they used to be in clear bottles. At one time they used to be set on people's steps, and if you get the morning sunlight or whatever, it can be very significant. What happens is the light actually breaks down one of our amino acids. And so you develop a character that you might call hay-like. There could be different descriptors for it. But it kind of starts off as being a dry hay, dry grass type character. And then a little bit more time goes by, lipid oxidation dominates. It kind of starts off with a hay-like note and then moves on to a very characteristic oxidized note. So those are light-activated reactions. Of course, beer, this is a very unique situation as well. I don't know if I mentioned, but I've taught in Otago University in New Zealand, and one of the things that we dealt with was off flavors, and we try to reproduce these off flavors. And I would tell them, okay, guys, you know what skunky is, right? Well, beer takes on a real skunky character. There aren't skunks in New Zealand. And they didn't have the faintest idea what I was describing to them about skunkiness. And so that didn't work so well. But any beer that has hops in it, so a beer that contains hops, and most do, a differing amount, those hops are unstable. They're chemically unstable to light. Light tends to break off a very weak bond. There's a nice little 5-carbon chain hanging off those hops, and that light will chop it off. As it chops it off, it leaves a nice radical. That radical interacts with sulfur to give you prenyl mercaptan, and it's the most beautiful skunk character you've ever seen in your life. It is just absolutely realistic. That is the chemical that skunks produce. It's produced in beer. If you want to test this, take any can of beer, take it a can. I'll make it a can because it's been protected, so there won't be any skunky flavor to it. Take that can of beer, open it up, put it in a glass bottle, put it out in the sunlight. Let it sit there for an hour. Then go ahead and have a smell of it. You'll be very impressed how skunky that truly is. Then somebody might raise their hand and say, well, wait a minute. Beer is sold in clear bottles. Most of it's in cans, brown bottles, or green bottles for a good reason, limiting light transmission. But some beers are sold in clear bottles that are exposed potentially to light. And in that case, they've either lived with it or they've gone ahead and take these hops, they extract the hops out of the hop plant, and they hydrogenate the hops. They chemically change those hops. They're not quite the same bitters, they're not quite the same flavor that the hops give the beer, but they change it in a way that we don't get the skunkiness. So the companies that do sell beer in clear bottles, either they try to protect it, or they go ahead and do an extraction of hops, hydrogenate the hops, and at least the off note is not skunky. It's something a little less, or a little more acceptable, I suppose I should say. Microbial growth off flavors, you bet. Lots of opportunity. You can have sour milk produced by microorganisms, and so what do you get? You get lactic acid, typical sour milk. There's all kinds of places where microorganisms come in and give an off flavor to a product. It can be the primary metabolism of those organisms growing in the product, or it can be residual enzymes in that product that give you the off notes. So again, microbial growth certainly is a problem that lead to off flavors. And it's interesting that when we think about this, and it can be after the organisms have died, it can be these enzymes that are left. So you might kill the organism at some point, but they leave enzymes. And so sometimes this total plate count isn't very helpful to you. You sort of find, oh, the organisms have all died. There's no microbial problem. But there's still some enzymes left from those organisms. So those are the major sources of off flavors. Bad things have happened to the food itself, deterioration of that food itself. When we talk about the second source of objectionable flavor, let me call it that, we talk about taints. So off flavors or taints. Taints are when the food has become contaminated. And there's lots of opportunity for that, lots of examples in books about how foods have become tainted. Taints can come through the air. They can be transmitted through the air into a processing plant, be absorbed by foods. That's especially true of baked products. They're fairly light. They tend to be baked. They then have to cool. They're exposed to the air during cooling. They're put in packaging that's sometimes pretty minimal because that baked good probably isn't going to have a very long shelf life. So you put basically very, very weak or very little packaging on it, and so they are prone to airborne contamination. But water can bring in off notes, and we'll talk about each of these. Disinfectants, detergents, and certainly packaging can bring in off notes. So we'll say a little bit about these. One of the common ones, oftentimes loading docks are where utilities, building utilities are put. And so you can have air intakes next to a loading dock. It's fairly convenient to put all your mechanical stuff of the building in this kind of construction loading area. And so diesel fumes, forklifts, or trucks parked out there. There may be a sign, don't idle your truck, don't leave it there. Use electric, of course, forklifts and so on. The idea of solvents, painting a room. I smile every time I see this. I smile because I'll explain. A food company, a meat producing company in Moncton, Canada, had a problem with tainting of their meats, and they called us and said, Gary, can you help us with this? Can you help us determine what has happened to that meat? It has a real chemical off note to it. Okay. So what I smile about, it was midwinter, and I didn't really want to go to Moncton, so I sent one of the graduate students. That's why I'm smiling, because it was kind of sneaky of me, or I should have gone and froze my butt off and sent one of my graduate students with. But what they had done is they painted, they had a holiday, they had some time, and so they decided, since the company wouldn't be staffed, there wouldn't be, like, they'd ship opportunity to do some painting. the painting was approved for use in food areas. And everything should have been fine except somebody stopped in and had one of the doors open for a bit. And those paint fumes permeated the meat. They had over $5 million worth of meat that was absolutely useful because the fat on the meat absorbed the paint fumes and you couldn't get rid of it. And they couldn't get rid of it. Nobody wanted it. Pet food companies, they rented trailers and had to store them over a year before they get somebody to take these things off. It was just a really fascinating problem. Another problem up in Superior, Minnesota, Duluth, Minnesota, a warehouse. And it was a refrigerated warehouse. And it's same type of thing. They wanted to do some painting of it. It was empty at that moment. It was warm. They painted it. But the guy who painted it, the floor should have been prepared better than it was. So there are cracks in the floor. And if you know refrigerated warehouses, they'll have a nice layer of concrete. Then they'll have insulation because you can lose a lot of heat down to the ground. So there's insulation and then more concrete. And so when the floor was cracked, the guy just put one more paint, right? Isn't that what we do sometimes? We fill the cracks with paint. Let's put a little more paint in. And again, this went to court, and when they showed pictures of it, there were places where that styrofoam, that 24 inches of styrofoam, was dissolved by paint. There was that much paint put in, kept on pouring it in. That warehouse has never been able to be used again for food. It was just this tremendous reservoir of solvents that's in the base of that building. So it's interesting. Because something says it's approved for food use in a food area does not mean it's safe from a tainting standpoint. There's absolutely no guarantee of that whatsoever. I could go on with examples about this. It's interesting. You have to be really conscious. This one here, neighboring industrial area. In this case, there was a bakery 25 kilometers away from a chemical manufacturing plant. And the aromas from the chemicals they were producing, this chemical plant, went through the air 25 kilometers and tainted the baked goods. And that's one that was almost impossible because it depended upon the weather. If the wind was blowing the other direction, the products weren't tainted. If there's certain barometric pressure in whatever, so air movement, that had to be a real miserable one to try to track down. 25 kilometers away, and it tainted the goods. So we've got a lot of chemicals out there that have very, very low sensory thresholds. People pick them up very, very easily. And you have to be very conscious of air movement opportunities. So air, you can say we could go on for that. Waterborne sources, residual cleaners, disinfectants left in the line. We use a lot of water in our manufacturing of foods. Very common. We wash things, we rinse them, we reconstitute ingredients. They can become a part of our food. So again, making sure that your water is clean and, like I say, no leftover disinfectants or cleaners in the lines. Actually, one of the first places I always look when we talk about off flavors in the manufacturing plant, I like to look at their water treatment because oftentimes people put in a nice water treatment, then they don't maintain it. And so your water treatment area becomes your contamination site. You get all kinds of nice microorganisms growing in there and giving off tainting type chemicals. So it's interesting. Water, boiler leakage, boiler contamination, cleaning boilers and not getting all of the cleaning agent out of them. Again, lots of opportunities. Packaging. And so packaging tends to be a scapegoat. When they don't find anything else, right away a person turns to packaging. You did it. And it's interesting. Nothing's ever done differently. Nothing's ever changed. The off flavor, the taint appears by magic. And so, okay, somebody has changed something. Something has happened. But it's oftentimes really hard to get documentation and get proof of it. Nobody wants to take responsibility for it. But some examples, again, of packaging, paper used as packaging. Contaminants in recycled paper shouldn't be used. Residual solvents in coatings of paper. You think about it, that I think one of the nicest examples of that was donuts. And the donuts were put in a nice clear cellophane wrap, but the donuts had white cardboard kind of crisscross, so the donuts would be separated from each other so they wouldn't get smashed. But you didn't really want those oily donuts to make that white cardboard greasy. That doesn't look very attractive when you open it up and there's an oil ring on this cardboard. So they basically put an oil barrier. They put a film on top of that cardboard divider that would keep it from absorbing oil. Well, that film is applied in a solvent, and they didn't let the solvent dry. So when they put the donuts in, they packaged it up, they packaged the solvent with it. When we took a look at that, we probably were thinking more about a fire hazard than anything else from the amount of residual solvent left inside those donut packages. Again, it's amazing. Residual solvents in ink systems, coatings and inks. In order to print on paper, in order to protect paper in various ways, very commonly there is some kind of a coating on the outside. And that coating has traditionally been in a solvent, and that solvent can be an issue to you. Inks. We're getting away from, let's say, hydrocarbon-based coatings. We're getting away from hydrocarbon-based inks, but now we're just adding a different problem to it. That's all. Except now it's an unknown problem. We've worried about and monitored all of these nice solvent-based materials for 40, 50 years, whatever number is. Now we got new materials. We're getting rid of hydrocarbons and we're introducing something else that is currently being studied. Adhesives. Again, every package has an adhesive on the top. The box of breakfast cereal, the case that the breakfast cereal came in, and there's been very little control of those adhesives. And they will migrate. They'll migrate from the adhesive into the box, right through the paper liner that your food is inside. Again, numerous examples of this. Plastic packaging is made up of monomers. You take individual chemicals and you polymerize them. Well, if you don't polymerize that plastic completely, which is really hard to do, you've got some monomers, off flavors, taints, I should say. So again, residual monomers in plastics is certainly an issue to us. In some cases, we've had certain types of packaging that break down at the pH of a food. So again, plastics, certainly a potential. The first TV dinners were placed on styrene trays. Everybody understands styrene. You smell styrene, you know it's plastic. And again, all kinds of problems from trays going in ovens and food being heated on them. Laminates, many of our packaging materials are, layer foil, layer polymer, layer paper, layer whatever. They got to be adhered together. There's an adhesive. Here we go again, more adhesives. Metal paper. This is, again, another example. If you might have seen a refrigerated dough product that's got a nice cardboard circle and there's a metal cap on the end. Well, to put those metal caps on, high speed, they tend to be lubricated, so there's some lubrication. And again, we've had situations where you open up those cans and there's enough solvents in there to be really obnoxious. So residual lubricants, residual hydrocarbons that might get incorporated into these products. Certainly metal cans. We've been visited last week by the major coating material for metal cans. The canning company and the company that makes the lacquer, the coating that goes on the inside of the can, came and visited us because they're getting the same thing. They're getting the idea we've got to get rid of hydrocarbons. We need to go to water-based things. We're having problems with them. But every food can has a coating on the inside. There's a chemical coating inside that can. It protects the food from the can and the can from the food. It goes both ways. Your foods are acid. They'll eat up that can. They'll attack that can. Your metals from the can will contaminate your food. And so, again, an opportunity through this lacquer, this coating that's put on. You find contamination in those coatings. You find they haven't dried properly. And so you can your product with the residual solvents that are in that lacquer. So again, lots of opportunity. Really our only really nice package and safe package for putting foods from an off flavor is glass. Glass does not contaminate a food product. The only problem you got to be careful with is you have to have a special opening on the glass, a special seal. So you need it like an ampule. You take a little file, you itch the top, you break the glass top off, you could pour it out. There's a little bit of tongue in cheek, okay? I'm not serious about that. But, there has to be a seal on the top of the jar. And that seal is a polymer seal. It's a metal seal. And so you have, again, even with glass, an opportunity for contamination. That rubber polymer seal on the cap. The coating that goes under the metal cap is an opportunity. So there are no packaging materials that are absolutely foolproof in terms of tainting. And it is thus a place that people look for sources of off flavors. How do we determine the source of the off flavors? I'm absolutely sold on sensory. Have somebody that's gone ahead and tasted these things, understand what happens to them. They will come in and they will tell you, the 99% sureness. This is what the off flavor is. That doesn't hold up in court. If it's somebody suing somebody else because how many millions of dollars of product was spoiled, that doesn't cut it. You need some instrument. Even though the person's typically right and probably the best source, you have to go to some analytical technique. Juries believe analytical numbers. They don't necessarily believe somebody saying, this is what it is. I think it's weird. It should be the other way around. But anyway. We start off always with sensory. And like I say, experience really helps a great deal. As I think I said, whenever we get an off flavor problem, the first thing we do is taste it. First thing we do is smell it. I was thinking of one case where the snow cone flavoring had a urine smell to it, and I was thinking, that's why I smiled. No, we didn't taste that. We just went by smell on it. So we'll taste or smell. How's that? The off flavor. It'll give us some ideas that'll tell us where we should go analytically. So let's say we can have a pretty good idea. This is the source of the off flavors. We go through a process. We try to isolate that off note, the chemicals responsible for the off flavor, do analytical separations, identifications by mass spectrometry, and then we've got a pretty good idea, if we can do this kind of identification, what's in that product that doesn't belong there. And by identifying the chemicals, you've got a really good idea of the mechanism. So that's what you do in court. If it's something that is in court, like I say, you can do it typically by sensory. If it goes for legal proceedings, you need to do this. So if in your analytical work you find a lot of new aldehydes, the ketones, you're typically talking about lipid oxidation. If in our analytical work you find branched chain aldehydes, they typically come from protein, amino acid breakdown from the Maillard reaction. So again, more than likely, it's the Maillard reaction. Acids, free acids, that's lipolysis, lipase enzymes, or perhaps microbial contamination. If we look at packaging, most of the things we find in packaging, we don't find in foods naturally. So they're unique things, unique materials that you normally don't find. So we look for solvents, we look for environmental chemicals that might be used one way or another. And so analytically, you go down, do these pathways, and come up with, let's say, typically a really good percentage. And so we can do quite well with determining the source of off flavors analytically if there's agreement on the character. What you get in trouble sometime is when somebody comes to you and you say, oh my gosh, I think this is tainted, flavor isn't quite right, I think it smells like cherries, benzaldehyde. George says, no, 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 that doesn't taste like that. It's not right, but it's more like skunk. Someone else says, I don't taste anything. When you get in those kind of things where you can't agree with it, it isn't pronounced, I usually don't take the job. How's that? You let somebody else worry about it. So anyway, let's move on. Our last topic is flavors and labeling. And you might say, wait a minute, this is food chemistry. I didn't get this approved, did I, George? I hope it fits in with your goals in one way or another. Because this is not chemistry. It's not food chemistry. It is something totally different, and like I say, labeling issues. So I want to deal specifically with flavors because I get more inquiries than you can imagine from newspapers, from journalists, from television, whatever, about artificial flavors and labeling issues. And so it's a common question that people run into. And the common question is, are artificial flavors safe? No, nature is safe. It's what they're going for, and that's the public opinion. And so it's something we respond to a lot. You as food scientists, experts in the field, should basically be knowledgeable. You should be able to respond to this. And that's why I want you to take a look at least give some thought to this. Labeling basically tells us what are we eating. It's interesting to me. When I was a new faculty member, I assumed that labeling was there for a purpose to inform people of safety. And little did I know at the time, but over time, labeling purpose is to tell people about something they want to know. It doesn't have to be a safety issue. If there's a concern amongst the population about the presence of monosodium glutamate, basically it gets on the label, not because it's unsafe. Many things are required on the label that have nothing to do with safety. They have interest in the public wants to know. So, like I say, when you see things being labeled or it's required as labeled, it's not necessarily logical from a science standpoint, but the public wants to know. Are you taking over? You can.
We're trying to figure out this thing.
Don't you want to get in line? Just go with them. Okay. So anyway, from a flavor standpoint, the issue, like I say, natural labeling of natural, and the public's right to know along those lines. It is interesting that if we look at food ingredients, the only food ingredient that is defined by law, what is natural and what is not, is flavorings. Colors, you talk about natural colors, there is no such thing legally as a natural color. If it's naturally colored, that you can't make that legal claim in that sense. And that's true of emulsifiers, it's true of any ingredient. There is no legal definition. Flavor is the only one. So when you see a label that says natural, all natural, they're taking a little bit of, let's say, non-legal freedom with that. And it's really pretty common. Who does define natural? That's always an interesting one to me. And we'll probably come back to that a little bit later on. So if not the law defining and our food ingredients, who does define natural? And we'll come back to that in the end. I think that's the last slide. So then we'll do this. Artificial, how do we know if something's naturally flavored, artificially flavored? And that gets down to our label. And that, of course, also goes with GMO-free, halal, kosher, take your pick. These are all issues that get defined on the label in one way or another. We're informing the population. This is the definition of natural flavoring. And if you'd, I don't know if you could read it in your slides or whatever. Basically, it is an extract from plants. So any kind of extract of plants. And so it can be a distillate of a plant, it can be a solvent extract of a plant, protein hydrolysate, roasting, product of roasting, heating, or enzymolysis. There's many different places that this can come from. They're not getting too far, are they? Anyway, It's interesting to me again. You look for inconsistencies. As a scientist, you think things should be consistent. They should be reasonable. And so, if we look at this idea, an oleoresin is an extract of a plant. You could take cinnamon, for example, extract it with hexane, evaporate off the hexane, and be left with an oil, a cinnamon oil. That material, by law, is natural as a flavor. But a material where you take olives and you solvent extract the oil from olives, that's not natural. Now, does that trouble you a bit? One food ingredient you can solvent extract and the industry says it's wonderful, it's natural. You take another material and it's not natural. Same process that goes on. I have problems with that. The idea of starch hydrolysates. Starch hydrolyzes very easily. It takes very little acid to hydrolyze starch. And that material is called unnatural. We take amino acids, we put them, or proteins, we put them in 6 normal sulfur or hydrochloric acid, heat the heck out of them, and that's natural. So proteins under 6 normal, heating the heck out of them, hydrolyzes them, it's a natural product. Do the same thing with starch, much, much less the starch, and it's not natural. So inconsistencies trouble me. But anyway, we're talking about flavors, right? Any product of fermentation, any product of enzymes, I can't necessarily see that from that standpoint. So again, this does define what is natural. And as long as a company lives by that, it's going to get a natural label. There is a rationale for this definition. There is a rationale for natural and artificial. And so when we talk about artificial natural issues with flavorings, it's really unique, a unique food ingredient. When you look at flavorings, if you want to get a strawberry flavor, you have to use exactly the same chemicals the strawberry does to make it taste like strawberry. You can't put other things in there. It wouldn't taste like strawberry. And so you must use exactly the same chemicals nature did, and you must use them in the same proportions. You can't put more, you can't put less of these. So if you want something to taste like strawberry, like cherry, like banana, like roast beef, whatever, you must use the same chemicals in the same proportion, and that is unique to flavor. If you put too much in, it doesn't taste good. And that's not true of any other food additive. No other food additive functions in the same way. We use many food additives that aren't found in nature. Or they're not limiting, self-limiting. But boy, if you put too much of a flavor in there, you notice it. You put too much of an emulsifier in there, you don't notice it. So there's not the same risks. And so every time I get hit up by a newspaper and talk about this, you try to say, well, look, this is a unique situation. And I go through this rationale with them. And they usually smile. It depends upon the paper and where they're coming from. And I think they go away happy. I come off with it's safer to eat artificial flavors than it is natural. And I will justify that to the article or the writer as well. In a cup of coffee, there's well over 900 volatiles that are produced. 267 of them are not approved for food use. They're not safe, or they're not known to be safe. If a company reproduces coffee flavor, they cannot use any of those 267 chemicals. They can only use the chemicals that are tested and proven to be safe. If you think nature's safe, let's go mushroom picking. I know nothing about mushrooms. We're likely to die at our first mushroom pick. You know, some of the best toxins in the world come from nature. So it's an interesting one. For the most part, you know, I agree with labeling and I agree with things, but when it comes down to flavors, they're a unique category. They really are. They're different from all other food additives in being self-limiting and requiring the same thing. So, in terms of label, you know the parts of the label. You've got the principal display panel. I'm going to show you some labels in principal display panel and talk about how these products are labeled. And then, of course, we've got information on the ingredient statement. So we get information from the main picture on front and whatever, and then back behind in the ingredient statement. And so this is Diet Right Cola. I could not get a decent image of this. I should have gone and taken a picture of it. You don't have the feedstock. It says natural and artificially flavored down at the bottom. I searched through every image I could find to get something that had good enough resolution to show, and could not find it. So what does this tell you? It tells you there's natural and artificial flavor components in this mixture. Uh-oh. Well, I thought that was for me. You know, I get drawn off the stage when it's time to go. I feel better, thank you. Anyway, so what do we have? It says, it tells the consumer on the front that there's both natural and artificial flavors. If we would look up at the ingredient statement, carbonated water, citric acid, you don't see that very well up there, natural artificial flavors, caramel color, potassium benzoate. What do we got? A number of preservatives in there. We have high potency sweeteners. We have red 40 coloring and so on. But it's interesting, it does tell us there's artificial flavors on the front. It tells us that because our label requires that we tell people as artificial flavors are present if they taste like the product. So they've added artificial flavors that are raspberry in character, so they must label as artificial flavors because they're raspberry in character. If they're not, if they don't resemble the name, they don't have to be. They can be artificially flavored, and they can say nothing on that whatsoever. It goes back in the ingredient statement rather than on the front panel. And that's the case with Golden Grahams. Golden Grahams contain artificial flavors, but there's absolutely no place on this front panel where it says they're artificially flavored. Ah, success is ours. Thank you. And so it's interesting, the first product had to label as artificially flavored. This one does not label as artificially flavored. Both of them contain artificial flavors because the artificial flavor added is not a Graham flavor. So interesting. Your product may be labeled, it may not be labeled, depending upon the character of the flavor. What do we have, another 2 minutes or less? 2? Okay, so we'll go for 2 more minutes. This says added lemon flavor. So this is a lemon lime. In this case, the product is naturally flavored, but the flavors that are added, the natural flavors, aren't necessarily from lemon or lime. And so up in our ingredients it says with other natural flavors. So we got flavor from lemon, flavor from lime, and other materials. It can be another pure chemical that's put in, that's been produced in a natural way. So it's interesting. Kool-Aid, what's its characterizing flavor? Punch? What's punch? You know, you could totally label that or flavor it with artificial flavors and never have to declare them on the front. You can put them just in back because only if they're characterizing, but punch isn't a character. So it can be totally artificially flavored with no mention whatsoever until you go to the back statement. This product, these nice truffles, nice package, you get a chance to go ahead and take a look at both of these. Lots of artificial flavors, but again, nothing on the front of that package. People are good about telling you if they're there. It's in the back panel, but sometimes you have to go ahead and take a look at it. This is the last slide, and it gets down to how do we label things. A lot of them are subject. Does it characterize? Doesn't it characterize it? And so oftentimes it comes down to corporate ethics. How we label that product. Do we put artificial flavors on the front or back? Whole Foods does a great deal. They set a lot of standards for our industry. So Whole Foods dominates labeling much more than the Food and Drug Administration does, or U.S. Department of Agriculture. They become the standard. Do you want to meet Whole Food standards? So it's a fascinating field. We find the public is having a hand in this as well. So anyway, time to close up shop. Thank you. It's been fun for me.
Thank you very much.
Have a good day.
So we meet on Friday and start with enzyme. you.
Well, it was close to.
Yeah.